In this section, we discuss how materials can change the direction and colors of light using reflection. You may recall from elementary optics the law of reflection, which is that the angle of reflection equals the angle of incidence. We define the angles relative to the vector normal to the interface. Snell's law similarly gives the angle of the transmitted or refracted wave as depending on the ratio of the index of refraction. These laws give the angles but not the intensity of the light. When light from a denser medium reaches an interface with a lighter medium, it bends away from the normal according to Snell's law. As the angle of incidence increases, a critical angle is reached where the refracted beam is parallel to the surface. Any greater angle will lead to no possibility of transmission or total internal reflection. In this underwater picture, the top surface of the water looks like a perfect mirror reflecting the image of the swimmer. Only when the angle gets closer to the normal can we start to see outside the water. Total internal reflection can be used to channel light in an optical fiber. This is a stream of water illuminated in the back with a laser pointer. The light stays within the stream even as it bends downward by total internal reflection. The same principle works in glass or plastic fibers. The light is channeled through the fiber by total internal reflection and guided long distances within the flexible fiber. The light escapes the fiber at the ends when the angle is closer to the normal. Optical fibers are now the best way to transmit digital information long distances for communications. Once you are willing to keep track of the polarization, one can also derive the relative amplitude of the reflected and transmitted waves relative to the incident wave. These are known as Fresnel equations. Exactly how the parallel and perpendicular polarizations are defined and used is described in the textbook. They give the relative intensity of the reflected and transmitted light depending on the angle of incidence, where the index of refraction along the polarization vector is used. The power of an electromagnetic wave is proportional to the square of the amplitude of the electric field. So the relative intensity of the reflected wave, known as the reflectance, can be determined from the Fresnel equations for each polarization. The transmittance is similarly defined for the transmitted wave. By conservation of energy, the fraction of light reflected and the fraction transmitted must add to unity. At normal incidence, theta equals 0, with light rays heading directly to the surface, the problem becomes symmetric and the polarization no longer matters. This greatly simplifies the Fresnel equations such that the reflectance simply depends on the difference in the index of refraction. For example, consider a typical glass window with refractive index around 1.5. The difference with air is 0.5. The sum is 2.5. The ratio of these is 1/5, or squared is 1/25 or 4%. Thus, about 4% of the incident radiation on an air glass surface will be reflected back, which also means 96% is transmitted. If the outside light is much brighter than the inside light, you will only be able to see the reflection, while someone inside will easily see outside. This is essentially how a one-way mirror works. This can be made even more effective by making the window more reflecting, say 80% with 20% transmitted. Now the unseen observers can have a little more light in their room, but don't turn off the light in the interrogation room or the tables will turn. One way to make a material more reflective is to make more interfaces. This can be used to make efficient dielectric mirrors that reflect all but 0.001% of the light, compared to a silvered metallic mirror which reflects 95% of the light. They can also be designed to partially reflect and partially transmit light for use as a beam splitter, mirrored sunglasses, or a teleprompter. The challenge with dielectric mirrors is that interference effects needs to be taken into account. The thickness of each dielectric layer must be designed to give constructive interference of the reflecting waves, which means the ideal thickness depends on the wavelength of the light. This leads to high reflectance, but only in a narrow band of light. The reflectivity of a dielectric mirror will also depend on the angle of incidence, where it doesn't for a metallic mirror. Dielectric coatings can also be designed to prevent reflection. Here, the film thickness is engineered so that the reflecting waves destructively interfere. This is used to prevent glare on glasses and screens, as well as improve efficiency of photovoltaic cells because more sunlight is transmitted when less is reflected by such means. A single thin film interference really only works for a particular wavelength of light, so it will actually look colored like a film of oil on a puddle where the various thicknesses of the film makes the rings of color. To make a good dielectric mirror or anti-reflection coating for white light, multi-layer coatings are better. Here is a multi-layer polymer containing hundreds of layers. It can be used to select which wavelengths you want to transmit and which to reflect. For example, in a window, you might want to reflect all the harmful UV from the sun as well as the infrared heat, but still let a good fraction of the sunlight in to brighten the building. Such windows can greatly improve energy efficiency as well as comfort. Interference effects can also be used to make bright colors, even in nature. Periodic optical structures are not limited to thin films in nature, but could be rods or particles with size scale near the wavelength of visible light. The morpho butterfly has chitin structures that give the blue iridescence. Silica spheres in opal make a periodic photonic crystal that leads to the coloration. The peacock tail feather has periodic melanin rods connected by keratin producing an inverse opal. The chameleon rearranges a lattice of guanine crystals to actively change coloration.